Okay, we are going to do some diploma style review for the chemical equilibrium unit. I have a sort of practice diploma on the left hand side that you'll see here. This is actually a diploma that was used in 2012 or 2013. So it is actually the type of questions and style of questions and format of questions that you would see in a diploma style setting. Now, I'm just going to go through a few questions. I'm going to take some time going through. If you feel the need to either fast forward to a different section or pause, please do so at any moment to ensure you're kind of following along with my steps and what I'm going through. And what I've done here is I've just taken the last chunk of the diploma exam, or the chunk with this unit on it, for you to take a look at and go through with me as I go through these questions, just so that we're not overwhelmed by the entire diploma itself. So I have the first question here is actually numerical response number 14. We aren't going to look at the multiple choice number 29 because it really doesn't have to do with this unit. It's with a previous unit or a unit that we're going to do later in this course. So we don't need to take a look at that quite yet. So numerical response number 14 says, if at equilibrium the concentration of sulfur trioxide is 0.289 moles per liter, the concentration of carbon dioxide is 0.018, and the concentration of carbon disulfide is 0.201, and the concentration of oxygen is 0.9. What is the Kc value? Now, I read the question first because it gives me an idea as to what I'm looking for. So I already know before I get confused with all the reading that I'm looking for my KEQ, or my Kc value. I call it KEQ. It helps me remember what I'm talking about here. So I have my products over my reactants. Sorry. Okay. So I'm going to take a look then at the information provided and see if there's anything else that's really vital to pull out of here for this question. So it says a technician places a sample of sulfur trioxide gas and a sample of carbon dioxide gas in an empty 1 liter flask and allows them to reach equilibrium at 800 degrees Celsius. The equilibrium system that is established in the flask is represented by the following equation. And then it gives me the equation. Now I'm going to rewrite the equation out just so I have it nice and big on this side of my work here. Okay, so when I know I'm calculating for my Kc or my KEQ, I know I have my products over my reactants. So I'm going to start by listing all my products on the top of my fraction here, and then my reactants on the bottom. So my products are carbon disulfide and oxygen gas. Now, these are all in the gaseous state, so I can include all of these entities because I can change the concentration of gases. Now, one thing that you may have gotten used to when dealing with acid and base equilibrium is that we can just write in our entities in this sort of expression, and it's just a 1-to-1 ratio, so it's no big deal. However, in this sample here, in this equation here, we have coefficients in front of some of our variables or our entities. So we need to ensure that when we write out our KEQ, or equilibrium constant expression, we need to include those exponents or those coefficients as an exponent in calculating our KEQ. So I have to ensure I have my oxygen to the exponent of 4, and same thing goes for my sulfur trioxide. I have 2 moles of that, so I have to include my 2 moles, and my carbon dioxide. So now that I have this written out, I like to write this out first so that I don't lose track of any exponents and I don't mix up products and reactants, etc. So this way it gives me a great visual just to take a look at my next step. So my KEQ then is going to equal, when I look over on my other side here, carbon disulfide, it says, is 0.201. No exponent on that guy. And when we look for oxygen, we have 0.9 with the exponent of 4. When we have sulfur trioxide, we have 0.289 And again, I'll erase this guy here. We have to the exponent of 2. And our carbon dioxide is 0.018. Okay, so when we go and plug all these numbers in here, I should get a value, hopefully when I do this right, I should get a value of about 87.7. And when I do plug that into my calculator, that is what I get when I solve and simplify this. Now, to ensure you're typing this into your calculator correct, make sure that you either solve for your top portion first and write that value down, say here on a different fraction, or when you plug it in, put this in brackets. Make sure you're multiplying this times this with the exponent, okay? And then put that whole thing in brackets, and then put this bottom section again in brackets. So when you do the mathematical function on your calculator doesn't get confused as to what you are plugging in. So we should get a KEQ value of 87.7. Now, this, when we're used to dealing with acids and bases, and we're used to equilibrium values with 10 to the exponent of -4 or 10 to the exponent of -10, this might seem incredibly large, and it is quite large. However, it's not an unreasonable number. So if you see a number like 87.7, don't be worried, okay? It also says record your 3-digit answer in the numerical response sheet. So we do expect there to be about 3 digits that we will record in our answer sheet. So this is a plausible number. Now, all that this larger number means is that we have significantly more products formed than we do reactants. So this is a reaction that favors our products. We have a great deal of products formed, which is all that means. Or in relation to our reactants, we have a great deal of products formed. So that's the answer to numerical response 14, 87.7. When we take a look at multiple choice question 30, it says, which of the changes to the equilibrium system numbered above would affect the equilibrium constant? So I'm just going to pick a new color here. So when we look at these 3 that are listed, it says the addition of a catalyst, decrease of volume. Okay, and remember, a decrease of volume in a container will increase the pressure. Okay, an increase in the temperature of the system. Now, when we're talking about an equilibrium constant, you might remember this from our Le Chatelier lesson, but the only thing that will actually change your KEQ value is a change in temperature. So remember, a change in KEQ is a change in temperature. So when we're talking about the addition of a catalyst, well, the addition of a catalyst won't change the equilibrium. It might change how fast you get to the equilibrium, but you still will reach the equilibrium at the same point. Okay, when you decrease the volume of a container, decreasing that volume, remember, increases the pressure. So if you increase the pressure, you shift to the side of the reaction with the smaller chemical amount. So if you are just shifting the equilibrium, you might shift it to a direction to produce more products or more reactants, but you really aren't changing that KEQ. So if you did increase the pressure, you shift to the side with the smaller chemical amount, which in this case would be your reactant side. However, it doesn't really affect our equilibrium constant. And when you increase the temperature, which is what we see here, it is the only thing that will change your equilibrium constant, making D the correct answer here. Okay, so only 3 will change that KEQ value. All right, let's take a look at another question. Okay, so it says, a technician injected fluorine gas and oxygen into an empty 1-liter vessel. She closed the vessel and allowed the reaction to reach equilibrium. Okay, this is the equilibrium equation that is given. So we have fluorine gas, oxygen gas, making oxygen difluoride. And it says, which of the following stresses represents the change in the equilibrium system at time x? So that's an important thing to keep track of, time x, on the graph above. So let's kind of just go through some of these possible situations and see if they make any sense. So it says a catalyst is added. Now, a catalyst added, again, will not change where an equilibrium is met. It will just change how fast. So potentially, if we saw a different set of data where this equilibrium at time x was met in a quicker manner than in another situation, then maybe we could think that the catalyst was plausible. But really, based on what we see here, we haven't increased the rate of anything because there's nothing to compare it to. So a catalyst being added doesn't really affect our shift in equilibrium, and it doesn't change our equilibrium constant. So we'll just put a line through that guy. Okay, so then it says pressure is decreased. Now again, if we decrease the pressure, we've increased the volume. So if we decrease pressure, we've increased the volume. And if we increase the volume, we shift to the side with the larger chemical amount. So if we increase the volume, we shift to the side with a larger chemical amount, which is actually our reactant side. So based on the graph here, we should see more reactants produced. So when we look at oxygen, oh, we see a decrease. Okay, well, let's check fluorine. We look at fluorine, oh, we see a decrease. So by pressure being decreased, we really shouldn't see less of our reactants. We should technically see more of our reactants. So I'm going to put a line through that because that guy doesn't really make much sense either. Okay, so when we have a temperature increase, okay, well, when we increase our temperature is this kilojoules, okay, it's an energy. Now, if we increase the temperature of this reaction, okay, we increase the amount of reactants. All right, now this is already an endothermic reaction, so if we increase our reactants, then we should see also an increase in our products, right? Our equilibrium, if we tip the scale, think of it as a scale or a teeter-totter, that if we tip that teeter-totter to produce more or have more products, we're going to produce more, pardon me, let me correct that. If we have a teeter-totter and we produce more reactants, we're going to create a system where our equilibrium is going to want to produce more products. So our equilibrium is going to want to shift to produce more of those products. So we should see a decrease in our gases here only because we're increasing a reactant that is not consumed. So we're increasing a reactant such as temperature, which isn't consumed, but these two are consumed to shift the equilibrium to produce more product. So if we see that, we should see a decrease in our oxygen gas, a decrease in our fluorine gas, yet an increase in our oxygen difluoride. So this is what we see. So we see that C is definitely a plausible answer. Okay, now I always like to check the last answer if I've gone through this many. I always check all four, just to ensure that I didn't catch myself on a question that was intended to trick me a little bit. So when I look, fluorine gas is removed from the vessel. So if I am doing something to take that fluorine gas out, if I remove these gas molecules, then I'm going to create a system that's going to want to decrease that stress. Okay, I want to oppose that stress. So if I remove fluorine, okay, I'm either going to lose some product or I'm going to want to increase the fluorine or increase my reactants in order to balance that out. So I should see either an increase in oxygen and a decrease in product, or I should just see some sort of shift to minimize the stress. So I should see a decrease in oxygen and, an increase in oxygen and decrease in oxygen difluoride. So that isn't what we see here. We actually see the opposite. We see an increase in oxygen difluoride and a decrease in our oxygen gas. So this guy also doesn't really make sense, which means here in this situation, 31C is the best answer there. Okay, now again, if this is something that you are confused on here, I would recommend going back to the Le Chatelier's lesson, rewatching some videos, and just getting a better understanding as to why our equilibrium will shift in different directions when different stresses are added. Okay. It says, use the following information to answer the next question. So it gives us a chemical equilibrium or equilibrium system with hydrogen gas, chlorine gas, and hydrogen chloride. And we look at any stresses, again, present. This is kind of similar to the last question that we saw. And we are going to try and figure out which of these stresses would cause the equilibrium to shift towards the products. Okay, so we want a shift that goes this direction. Okay, so when we take a look here, it says the addition of H2 gas, the addition of HCl gas, the cooling of the equilibrium system, and an increase in volume of our container. So we'll take a look at these a little bit more in depth, and we'll take a look at which ones maybe would make sense to change this equilibrium system. So the addition of H2 gas is the addition of reactant. So if we increase the amount of our reactant, okay, we would cause an increase in the product. So if we increase reactant, we increase product. So number 1 should give us a shift to give a shift towards the product side or a shift towards the right. Okay, so this one shifts towards the right. So I'm just gonna notate that by an arrow towards the right. Okay, the addition of HCl, okay, it's a little different. We're increasing the amount of product. So if we increase the amount of product, we actually increase the reactants to balance that change. We've tipped the teeter-totter. If this is our teeter-totter, we've tipped it this way. We've increased the products and decreased the reactants. Well, we want to shift that back up. So, pardon me, the addition of HCl would shift the equilibrium to the left. Okay, the cooling of the equilibrium system. When we look at this value here, the cooling, if we decrease the temperature, now this is where the temperature in Le Chatelier's is a little bit funny because we have to consider both if it's an exo or endothermic reaction. In this case, since heat is produced, heat is released, it is an exothermic reaction. So if we cool this system, we're actually pulling heat away. So we're decreasing the amount of products. So if we pull products out, we've shifted the equilibrium in the other way. Okay, if this is our teeter-totter, we've pulled products out, and we want to minimize that change to increase the amount of products. So this will actually cause a shift to the right as well, to our products as well. Okay, by increasing the volume, again, remember when we increase the volume, we decrease pressure. Okay, so we decrease pressure for number 4. Okay, when we decrease pressure, we shift to the side with a larger chemical amount. Well, we have 2 moles and 2 moles, so really an increase in volume will not change our shift in equilibrium because there's 2 moles on either side, which means that it doesn't affect the equilibrium, because if you were to increase or decrease pressure, it really doesn't change or shift the equilibrium in any way, because there's 2 moles on each side. So this is a null. It doesn't really affect this equilibrium for this particular system. So when we look at the 2 that have a shift to our product side is 1 and 3 only. So question number 32A is the best answer there. Okay, let's take a look at this example here. So it says the equilibrium constant for the reaction represented by the graph above is blank. So we are going to look at our numerical values and on the graph and see if we can calculate some sort of equilibrium constant. Now I'm going to do this on my space on the right just so I have lots of room here to write this in. So let's just read this information and we'll see what we can pull out of it, see what we can get. So a technician is producing hydrogen gas. He adds methane gas, steam, and nickel catalyst. Okay, nickel catalyst isn't part of our reaction. Remember, it's just a thing to help this reaction move forward in a timely fashion. Okay, and it's to an empty container to allow the system to reach equilibrium. The reaction is represented by the following equation. So it says the technician's data is represented by the following graph, and he has the graph here. So once you see no more changes or no visible changes in the concentration, okay, you will see that that's when the system has reached equilibrium. So when we are calculating our KEQ, remember KEQ is our products over reactants. Remember that? Always, always, always. Okay, and when we look at our products of our equation that was actually given to us here, okay, our products is my hydrogen gas to the exponent of 3, my carbon monoxide, my methane is a reactant, and my water is a reactant. Now, because water is a vapor, it's a gas, I can include it in my equilibrium system. Don't get tripped up because we don't include water with our acids and bases. When it's a liquid water, we do not. When it's gaseous water, we do include it. So make sure you include that in your equilibrium system. Now, when we go to fill in these values, we simply pick the values off the chart. So for my hydrogen gas, my value or my concentration of that, it looks to be, well, in between 1.6 and 2.0. It appears to be a sort of 0.2 jump every time. So 0.2, 0.4, 0.6, 0.8, etc. So between 1.6 and 2.0 should be 1.8. And don't forget that we're cubing it. We have it to the exponent of 3. Okay, my carbon monoxide is at equilibrium. If we go over to the right here, or the left, pardon me, it's 0.6. And methane is 0.4. And our water vapor is at a 0.2. So when we go to plug all of these numbers in, we have to ensure again that we sort of follow our mathematical functions. We have to do the top of our equation followed by the bottom of our equation when we're solving this. So when I go 1.8 to the exponent of 3, let's plug that into our calculator, times by 0.6. This equals okay, I can keep that in my calculator. If I have a scientific calculator, I can store that value. Okay, and I'm going to divide that by 0.08 because that is 0.4 times 0.2. And when I simplify that even further, I get a value of 43.74. Now, I have to look at what the question is asking me. It says record your 3-digit answer, which means that I will record 43.7 in my numerical response answer sheet on my diploma. So 43.7. When I check my answers, it does look correct. So you should get that answer as we go through. Now, please don't forget your exponent here and to put this in brackets. If you're simplifying this on a calculator, make sure you have your numerator and your denominator in brackets each so that we're not dividing by 0.4 and then multiplying by 0.2. You're simply dividing by this 0.08. Okay. We'll continue to look through some questions here. So we'll look through, how many more questions do I have here? We will take a look through question 33 and numerical response 16. So it says the concentration of aqueous hypochlorite in laundry bleach. Oh, let's just take a look here. Okay, perfect. So the pH of the solution changes from a 9.2 to a 7.2, then the acidity of the solution either increases or decreases, and the hydronium ion concentration increases or decreases by a factor of 100. So when we take a look here, we will see that we have our hydrogen on my left-hand side, and we're talking about the acidity of the solution, and we are looking at the pH change from a 9.2 to a 7.2. So when we see a 9.2 to a 7.2, this is sort of more on the basic side to more on the neutral side, but still we are increasing the acidity. We increase the acidity. We've gone on a lower pH scale. So A and B automatically not good answers. Okay, so we increase the acidity and the hydronium ion concentration. Well, our hydronium ion concentration is this guy, and if we increase the acidity, this number or this concentration then also increases. So if you increase acidity, you increase H3O. If you increase basicity, or the basic properties of a substance, you are going to increase the hydroxide ion concentration. So as long as we keep track of what is our hydronium ion and that our pH scale, a low pH is a very acidic solution, then we're good. Okay, so then numerical response number 16. A sample of hydrogen iodide gas is collected and then dissolved in 10 liters of water. Okay, so then it says statement about solutions. So it says the question is asking the statements above that describe hydrogen iodide solution are numbered blank. So, okay, let's take a look. The pH is less than the pOH. Well, let's take a look. We have hydrogen iodide. Oh, I'm going to do this on my next page here so I have a bit more room. So I have my hydrogen iodide dissolved in water. And remember that if we do that, we create H3O and I-. Okay, hydrogen iodide in a solution is very, very acidic. It's one of our strong acids. So the pH is less than the pOH. Oops, it's the wrong one. There we go. We do expect the pH to be less than the pOH. So we do expect number 1 to be true. Okay, the pH is greater than the pOH. Well, we know that that one isn't the case. Okay, the solution conducts electricity. Because we have ions present, which we see here, we see our ions present as our H3O and iodide, we do expect it to conduct electricity. Based on acidic properties, all acids should conduct electricity. Okay, the solution does not. Well, I crossed that guy out. Almost all of the HI ionizes. We do, because it is a strong acid, we expect that the hydrogen iodide ionizes almost entirely, or it does entirely ionize in the solution to form 100% H3O and iodine. Now, the reason I know that is it's because it is a strong acid. It's one of our 6 strong acids that we'll see on our data booklet that's listed sort of above that gray bar. So we know it's a strong acid. We should have 100% ionization, or close to 100%. Okay, so 6 is not the case. Then it says the concentration of H3O is less than the concentration of OH. Okay, I would say that because it is a very acidic solution, we expect there to be lots of H3O. So 7 doesn't sound so good to me. And then 8 says the concentration of H3O is greater than the concentration of OH. I would say that sounds a lot better. And it is an acidic solution, so we'd expect there to be lots of H3O, not a lot of OH. So our numbers then are listed as 1, 3, 5, and 8. Now, when we go to list these numbers, try and write them in numerical order. It will tell you if you have to write them in numerical order, but if it says in any order, it doesn't matter how you write them down. But I like to get into the habit of writing them down in numerical order just to keep track of what I'm doing here. All right, so those ones are a bit faster, so let's keep on plugging away here. So question number 34, it says, the following equilibrium system maintains a constant pH in the intercellular fluid in the body. Okay, it says the Bronsted-Lowry acid in the equilibrium system represented above is blank, and it will donate protons or something to the base. So we're talking about, our Bronsted-Lowry acid and our Bronsted-Lowry base. So in this case, we have our acid here and our base, and here we have our acid and our, I mixed that up a little bit. We have our base, which is our proton acceptor, and our proton donor is our acid here, and then that forms our acid and our base on the other side. So it says the Bronsted-Lowry acid is going to be our H2PO4 minus, okay, and that donates protons to our Bronsted-Lowry base. So the correct answer here is C. Now, if we were talking about our product side going to our reactant side, in fact, this would be the acid. However, that's not an option that's listed. So when we're dealing with our Bronsted-Lowry reactions, we usually look at our reactant side of our equilibrium, and those were the entities that were listed were both of our reactants, so the only one possible is C. So the next question, again, going back to 34 here, just remember that acids are proton donors and bases are proton acceptors. So that should help you both label these entities and also to figure out either the products, if this is correct, and also just will help you solve this, actually, the second part of this question here. Okay, 35. Which of the terms numbered above can be used to describe the reaction or the species in the reaction system above? So it says use the following additional information. Okay, this is some important information even that's given above those questions to help us solve these. So it says the additional information to answer the next question. So which of the terms numbered above can be used to describe the reaction or species in the reaction in the equilibrium system above? Okay, so it's either a buffer, it's amphiprotic, it's polyprotic acid, polyprotic base, and a conjugate acid-base pair. Okay, I would say that when we go through here, we have a buffer. Now, a buffer is a system where you have a conjugate acid and a conjugate base in a system in order to minimize the changes in pH. So if we would have for example, H2PO4 minus and HPO4 minus, okay, these two things would be a buffer system to minimize the change. Now, if we were to add an acid to this, we could form this conjugate acid of the HPO4 minus to minimize the change into a base. So we could actually consider this a buffer. So we can check that guy off. We have small amounts or amounts of sort of the conjugate acid and the conjugate base buffering each other to minimize that pH change. Again, remember, it's only buffers. We only talk about buffers when we're talking about weak acids or weak bases or both. Okay. Amphiprotic. Well, definitely these entities are amphiprotic. H2PO4 can both donate a proton as well as it has a negative charge, so it can accept a proton, as can our HPO4 minus. It can still donate this proton and it can still accept a proton as well. Okay, so amphiprotic, absolutely. Polyprotic acid. Definitely we have a polyprotic acid. H2PO4, polyprotic. It has more than one proton. It has two, in fact, so we can check that off. It has more than one, we're good. Polyprotic base. Again, this base can be removed more protons or add more protons. Neither sense. It's a polyprotic base for sure. Okay, and a conjugate acid-base pair, well, our conjugate acid-base pair is either those two or those two, in which case we have a conjugate acid-base pair. So our correct answer here is D. Now, I think I'm going to stop. Where should I stop? I think I'm going to stop here, and I'm going to make a second video for the rest of this review section, so that if you wanted to go over sort of these few and then go back and check your answers and check with a friend, etc., you can do so now. And then the next few questions I will do in a separate video where we can go through, and it's not such a long stretch of video, and we can sort of divide it into two chunks. Okay, well, good luck. Hopefully you were able to follow everything. Like I said before, if you feel the need to pause the video or rewind or go back, please feel free to do that now and double check your work, double check your answers, and make sure you're following along as to what I'm talking about when we go through these questions. All right, good luck.